Good evening, Professor. My name is Pablo Copa, and today I will present my project titled Time Series Analysis of Sunspot Activity using R. In this presentation, I will explain the work I completed for week 7. The main purpose of this project was to, excuse me, was to analyze monthly sunspot activity over time using R. I will explain the steps I follow, the results I obtain, and how these results can be connected to a real-world business situation. For this project, I work with a dataset that include monthly sunspot observations starting from the year 1749. This was useful because time series analysis works best when data is organized across the time. Since the dataset covered many years, it allowed me to observe long-term behavior, repeated patterns, and change in solar activity. I'm still learning R, so my focus was on applying basic functions correctly and understanding what each result meant. I used tools such as data loading, summary statistics, time series formatting, plots, moving average, decomposition, and autocorrelation. As I explain each slide, I will first describe what I did, then I will explain what the graphs or results shows, and finally I will connect the findings to decision making for a wireless carrier company. The main idea is to show how even basic art tools can help to transform raw data into useful business information. The objective of this project was to analyze monthly sunspots activity over time using R. The dataset contained 3,000 to more than 3,000 observations beginning in 1749, which made it a good example for time series analysis. Because the data was organized by month, I was able to study how sunspot activity changed across many years. To complete the project, I follow a simple process. First, I loaded and explored the dataset to understand what variables were included. Then, I transformed the sunspot values into a time series object so R could recognize the data as monthly observations over time. After that, I created graphs and applied basic tools such as a moving average, decomposition, ACF, and PACF. The reason I used this structure was to move step by step from basic data understanding to deeper analysis. I didn't begin directly with graphs because I first needed to confirm that the dataset was correct. Once the data was ready, I could begin looking for patterns. Since I'm still a beginner with R, I focus on clear interpretation instead of advanced forecasting. However, even with basic tools, I was able to identify repeated cycles and a strong related behavior, a strong time related behavior. This project is important because it shows how historical data can help us understand patterns and in a business context, especially for wireless carriers, identifying patterns in solar activities could help companies prepare for possible signal interference and improving planning. In this step, I loaded the Sunspots database into R. I used the readx1 package because the file was provided in Excel format. After loading the data, I used the head function to display the first rows and confirm the and confirm the sorry, Professor, it's already evening and I'm a little tired. And confirm that the data set was imported correctly. Uh, this step was very important because before doing any analysis, I needed to make sure that the file was readable, and the main variables were available. It took me few minutes. I had to watch videos on YouTube to know how to import that data into R because the the website that was provided didn't have that specific part. So let's go back. The dataset included so when we add all these formulas, the dataset included three columns, an index column, a date column, and the monthly mean total sunspot number. The most important variable for my analysis was the monthly sunspot number because that was the value I needed to study over time. After loading the data, I also explored the structure and summary statistics. The dataset had 3,265 observations. The average sunspot was about 81.78, and the maximum value was 398.2. This showed me that the data had a wide range of values. Some months had very low sunspot activity, while others months had very high activity. This was my first indication that sunspot activity changed significantly over time. In simple terms, the data was not flat or constant. It had a strong variation, which made it appropriate for time series analysis. This step helped me to confirm that the dataset was ready for the next stage of the project, which is preparing the time series object. So after loading and exploring the dataset, I converted the sunspot values into the time series object in R. I used the TS function for this step. And I selected the column that contained the monthly mean total sunspot number. Then I defined the starting point as January 1749. I also used a frequency of 12 because the data was monthly. This step was very important because R needs time series data to be structured correctly before applying certain time series tools. Before this step, the sunspot values were just a column of numbers in a table. After this step, R understood that the values as I mean R understood the values as observations connected through the time. The starting point wa- uh, the starting point was the formula start equals C parentheses 1749,1. This starting point told R that the first observation began in this specific month. The frequency of 2 told R that there were 12 observations per year. This allowed the data to be treated as a monthly time series. From a beginning perspective, this was one of the most important steps because it changed the dataset from a regular data table into something that could be analyzed over time. Once the object was created, I could create graphs, apply smoothing, decompose the series, and analyze autocorrelations and all the kind of forecastings. This step prepared the foundation for the rest of the analysis. Without converting the data into a time series object, the later visualizations and time-based analysis will not have worked correctly. This slide shows the first main graphic of the sunspot data. The time series the time series plot displays how the monthly mean total sunspot number change over time. When I look at this graph, I can see that the values rise and fall repeatedly across the year. At first, the graph might look very busy because there are many observations, right? However, the main pattern is clear. Sunspot activity doesn't stay constant. It moves through repeated periods of high activity and low activity. This tells me that the data is not random. Instead, it follows a cyclical pattern. This finding is important because the graph gives visual evidence that sunspot activity change in a structured way. Some periods show very high sunspot numbers, while other periods drop close to zero, as you guys can see. These repeated peaks and troughs suggest that solar activity follows long-term cycles. In relation to the real world, this matters because sunspot activity can affect communication systems. Higher solar activity can create can create interference that might affect wireless signals, satellite communications, or radio-based systems. For a wireless carrier, this means that solar activity is not just a scientific topic, it can become an operational concern. This graph also helped me to understand the big picture. It showed me that the dataset contained meaningful time-based patterns, which justify continuing with something smoothing, decomposition, and autocorrelation analysis. Applying a 12 monthly average. In this slide, I applied the 12-month moving average to the sunspot time series. The original time series plot had many short-term movements because the data was monthly and covered many years. Because of that, it was difficult to focus on the broader pattern. The moving average helped me smooth help smooth the data and made the long-term trend easier to see. The red line in the graph represents the 12-month moving average. Since the data is monthly, using 12 months makes sense because it summarizes a one full year at a time. This helped me to reduce some of the smaller monthly fluctuations and allowed me to focus on the general movement of sunspot activity. When I look at this graph, the cycle becomes easier to understand. The red line shows the sunspot activity rise and falls over the long periods. This confirms what I saw in the regional time series plot, but in a cleaner way. From a business perspective, this type of smoothing is useful because companies usually do not make decisions based on a very small monthly change. Instead, they often look at broader trends. For a wireless carrier, the moving average could help identify periods when solar activity is increasing or decreasing. This step helped me move from a noisy graph to a clearer, clearer, clearer view of the data. It made the patterns easy to explain and help connect the analysis to planning and decision making. Time series decomposition. In this slide, I use time series decomposition to break the sunspot data into different parts. The decomposition is separate the data into observed values, trends, seasonal patterns, and random variations. This helped me to understand what was happening inside the time series instead of only looking at the full graph. The observed part shows the original data. The trend shows the longer term movement of sunspot activity. The seasonal component shows repeated patterns, as you guys can see, and the random component shows variation that is not explained by the other parts. When I look at it at first sight, it looks crazy. When I made this graph, I knew what I was looking for, but the results of this graph was more than enough. So when I look at this decomposition graph, I can see that the data has a strong structure. The trend component shows a smooth long-term waves. I think they call it like that, long-term wave, which means sunspot activity moves through extended cycles. The seasonal component also shows repeated behavior. Repeated behavior. The random part is present, but it does not dominate the full series. This is important because it confirms that most of the movement in the dataset is not random. The data has repeated behavior that cannot be studied, that can be studied and monitored. From a beginner perspective, the composition helped me to understand the series in a simpler way because it separates a complex graph into smaller parts. For a wireless carrier, this matters because structured patterns are easier to plan around. If solar activity follows repeated cycles, company can monitor those cycles and prepare for periods of higher risk. This supports better operational planning and reduces the chance of being surprised by signal related issues. In this slide, I will be a little bit short because it's almost 50 minutes. I analyzed the ACF and graphs, the ACF and PACF. These graphs help me to understand how current sunspot values are related to past values. In simple terms, they show whether the past still matters when trying to understand the present. The AC graph shows autocorrelation across different lags. When I look at the ACF, I notice that correlations decreases slowly. This means that the data has memory over time. In other words, the past continues to influence later values. This supports the idea that the data is not random. The PACF graphs gives a more direct view of which recent past values are most important. In my result, the first few legs were strong, were the strongest. This means that the recent values had a stronger direct relationship with current sunspot activity than older values. For a wireless carrier, this can support planning. If recent samples activity is high, the company might monitor conditions more closely. If the pattern suggests increasing activity, the company can also prepare for possible signal interference. ACF and PACF results support the idea that the time series models could be useful for forecasting solar activity. Business applications. The business applications for this analysis are important because the results are not only statistical, they can also be connected to real-world decisions. In this project, I imagine the situation of a wireless carrier that is concerned about signal transition and possible interference caused by solar activity. The analysis showed that sunspot activity follow repeated cycles. This means that a company does not have to treat solar activity as completely unexpected. Instead, it can monitor historical patterns and use them as part of planning. For example, so this is especially relevant today because people and businesses depend heavily on wireless communication, internet connectivity, GPS, and satellite-based systems. Even small disruptions can affect operations, customers, and service quality. For me, the key lesson is that time series analysis can help transform historical data into practical information. Even simple art tools can help identify risk periods and support better planning. Conclusions and limitations. In conclusions, this project helped me to understand how to analyze time series data using R. I start by loading and exploring the dataset and convert it into time series project. After that, R allowed me to create graphs, apply a moving average, and analyze ACF and PSV. The main finding was that sunspot activity follows repeated cycles over time. The moving average made those cycles easier to see. That the composition showed that the data had trend and repeated structure, and the ACF and PACF showed that the past values were related to present values. From a business perspective, these results can help wireless carriers prepare for possible signal disruptions during periods of high solar activity. The analysis supports the idea that historical data can help companies plan ahead. In future work, There were also limitations. I used basic techniques because I'm still learning R and time series analysis. I did not use advanced forecasting models such as ARIMA or other machine learning tools. Also, the analysis only used historical sense of data and did not include other variables that may affect signal transmission. Thank you very much for your attention. Good night.